Welcome back. This is going to be the first of two video lectures covering section 3.3 of the textbook, the inverse of a matrix. Now I've broken section 3.3 up into 5 parts. What is an inverse? Properties of invertible matrices, elementary matrices, the fundamental theorem, and finally computing the inverse. We're going to cover these first 2 topics in this first video lecture, and we'll save these remaining 3 topics for the second video lecture. So let's begin with the question, what is an inverse? Now before we answer this question for a matrix, it's helpful to think about the notion of an inverse in other contexts. So first, let's solve the equation 3x equals 8 in the real numbers. And second, let's solve the equation 5x equals 2 in Z7. So join me at the document camera to look at the solutions to these problems. All right, welcome to the document camera. We've got 2 problems to solve. First, we want to solve the problem 3x equals 8 in the real number system and 5x equals 2 in Z7. So we're looking for a real number such that 3 times that number equals 8. And we're looking for an element of Z7 such that 5 times that number gives me 2. Now, let's look at this problem first because this will look very familiar. We would typically think of solving this problem by dividing both sides by 3, and there is something right about that. On the other hand, what I really want us to focus on, especially in light of where this is going, I want us to think about solving this problem by multiplying both sides by the multiplicative inverse of 3. I want us to think about what we could multiply both sides of this equation on to turn the 3 into a 1. And that number is what we typically call 1/3. So what I want to do in this equation is multiply both sides by 1/3. Now on this side, we can use the associative property of multiplication and rewrite this as 1/3 times 3x equals, and this side we can just render as 8/3. Okay? Now, 1/3 times 3 is just 1. That's the property that 1/3 has. It's the multiplicative inverse of 3. So 1/3 times 3 is 1. So this is 1 times x equals 8/3. And 1 in the real number system has the property that when 1 multiplies any number, it's just the number itself. So we finally get the solution, x equals 8/3. Okay, so what I want us to think about, especially in terms of where this is going, is let's think about solving an equation like this in terms of multiplying both sides by a multiplicative inverse. Now, one thing I want to point out is if this equation had come to us as find the number x such that x times 3 is equal to 8, we wouldn't think of that as a separate problem. We would see that that is just the same problem being given to us in a slightly different form. And that's because multiplication in the real numbers is commutative. So x times 3 and 3 times x are the same thing. And so we don't think of this as a separate equation. All right, I want to plant that thought in the context, thinking about equations involving matrices. I want you to see that there is no distinction in the real number system, but there might be a distinction in terms of a matrix equation. All right, now let's look at this problem. And now let's think about it in terms of this multiplicative inverse strategy. What I want to imagine is getting x by itself by multiplying both sides by something that will turn this 5 into a 1. And this is now in the Z7 context. So we have to think of what is the multiplicative inverse of 5. And there aren't that many numbers to go through. You can check 0 through 6. You're just looking for something that multiplies times 5 and gives us 1. And just by poking around or by consulting a Z7 multiplication table, you'll see that that's the number 3. All right, so what I want to do is multiply both sides of this equation by 3. Now again, we're working in the Z7 sense. So we've got 3 times 5x equals 3 times 2. Now I'm going to reassociate. And 3 times 2 is 6, and that's true even in Z7, so I can just write that as 6. And now 3 times 5, in conventional arithmetic, that would be 15, but in Z7, we would look at that remainder, and that's 1 more than 14, so this is just 1 in Z7. And 1 in Z7 has the property that it multiplies by anything and gives us that thing itself. So this is just x equals 6. And so there's how we would approach solving this equation in the Z7 sense. We'd use the multiplicative inverse of 5. And just as here, because multiplication is commutative in Z7, whether this equation came to us as 5x equals 2 or as x times 5 equals 2, there's no difference, right? Because we could easily think of x times 5 as the same as 5 times x, and there would be no difference in this equation or versus this equation. Okay, all right, so that kind of sets us up. We already can think of solving simple equations like this, whether in the real numbers or in Z7, by this process of a multiplicative inverse. And the question that sits before us now is there such an object in the matrix world? Is there such a thing as a multiplicative inverse? Well, that's what we're going to talk about in our lecture today. So let's head back to the class notes and dig into that concept a little bit. Now let's think about solving some elementary matrix equations. And remember that matrix multiplication is not commutative. Thus, there are really two types of elementary matrix equations, and I'm just going to call them A on the left and A on the right. So let me explain what A on the left means. So given matrices A and B, find an unknown matrix X that satisfies the equation AX equals B. So we're solving for this unknown matrix X. We want to know what is this matrix X that would satisfy this equation, but we see the multiplication by A now is on the left. So we would have to solve the equation AX equals B. We also have a version where A is on the right. So given matrices A and C, find the unknown matrix Y that satisfies the equation Y times A equals C. And here we see the matrix A appearing on the right. Now, because matrix multiplication is not commutative, these are different equations. I cannot simply take the A and the Y, commute them, and turn it into an equation of this form. It's a fundamentally different equation. And so we'll have to adapt our way of thinking about solving these matrix equations accordingly. Now let's think about how we would solve each of these types of equations. And let's begin with a case where A is on the left. So once again, we have to imagine A has been given to us, B has been given to us, and we're trying to find this matrix X that solves the equation AX equals B. Now what we would like is some means of canceling the matrix A that appears on the left-hand side of this equation. So in this case, we're looking for a matrix, let's call it A prime, that has the property that A prime times A is equal to the identity matrix. And we're going to call that a left inverse for the matrix A, because when I multiply A by A prime on the left, I get the identity matrix. All right, now let's see how that can be useful in solving equations. So I can begin with my equation AX equals B, and I can multiply both sides of that equation on the left by A prime. Now, matrix multiplication is associative, so I can pull up these parentheses and reassociate them and think of this now as the multiplication of A prime times A first, and then by X. But because A prime times A is equal to the identity matrix, this is just the identity matrix times X on the left. And finally, by a property of the identity matrix, this is just X on the left. So if we have such a matrix A prime, we can write our solution as X equals A prime times B. So if we have a left inverse, then we can solve this equation as X equals A prime times B. Now let's contrast this with what we would have to do with an equation in which A appears on the right. Now we're trying to solve an equation of the form Y times A equals C, where Y is the unknown matrix. What's this matrix Y that satisfies the equation Y times A equals C? Now in this case, I claim we're looking for a matrix A prime that has the property that A times A prime is equal to the identity matrix. This is what's called a right inverse for the matrix of A. All right, A times A prime equals the identity. Now, let's see how we can make use of this right inverse for A in solving an equation of this type. What we're going to do is multiply by A prime on the right side of both the left and the right sides of this equation. So we're going to get YA times A prime is equal to C times A prime. In other words, A prime is appearing on the right on both sides of this equation. Now, once again, matrix multiplication is associative, so I can lift these parentheses off and reassociate them and think about this as y times A prime. A times A prime, of course, is the identity matrix. That's the role of the right inverse. And we know that matrix multiplication, when doing matrix multiplication, that y times the identity matrix is just y. So, armed with this right inverse, we could solve this equation as y equals C times A prime. Y is equal to C times the right inverse of the matrix A. For our work, we're looking for a matrix A prime that is simultaneously a left inverse and a right inverse for the matrix A. And this is a much stronger condition. So, given a matrix A, we want a matrix A prime that satisfies A prime times A equals A times A prime equals the identity matrix. Now, a moment's thought will show you that in order for this to be true, in order for such a matrix A prime to even exist, A would have to be a square matrix, and A prime would have to be a square matrix of exactly the same size. Now, this leads us to the following definition. If A is an n by n matrix, an inverse of A is an n by n matrix A prime with the property that A times A prime is equal to I, A prime times A is equal to I, and I is an n by n identity matrix. Now, if such a matrix A prime exists, then we say that A is invertible. So, whether or not A is invertible depends on whether or not a matrix A prime exists that satisfies both of these equations. And as we shall see, some matrices are invertible, some matrices A have inverses, and others do not. Let's work a problem together. In each case, determine whether the matrix A is invertible. If it is invertible, find an inverse. So I've got two matrices A, two candidates here set up for us. Let's go to the document camera and explore each of these matrices to see whether or not it's invertible. And if it's invertible, can we find an inverse matrix? So let's head over to the document camera and investigate these examples. All right, welcome to the document camera. In each case, we want to determine whether the matrix A is invertible, and if it is, find its inverse, or find an inverse. Now, what I'm going to do is first, I'll work this problem first. I'm going to test to see whether I can find a matrix that will multiply on the right and produce an identity matrix. If I'm successful in doing that, I'll flip it around and see if it also multiplies correctly on the left. So I'm just going to pick one side. I'm going to pick the right, and I'm going to see, can I find a matrix? Let's say its entries are A, B, C, and D. So when I do this multiplication, I get the identity matrix. All right, let's work on this left-hand side a little bit. This can be reduced to a 2 by 2 matrix. Let me give myself a little grid to work in to keep myself lined up here. So the first entry, the 1, 1 entry will be 2A plus C. And then in this first row, second column, 2B plus D. 0 plus 3C. And then finally, 0 plus 3D. Okay, now, if these matrices are going to be equal to each other, they, of course, have to be equal entry by entry. And so this is going to give me 4 equations in the 4 unknowns. 2A plus C equals 1. We're also going to have 2B plus D equals 0. 3C equals 0. And 3D equals 1. Now, luckily, this system kind of degenerates very quickly and separates. We can see immediately from, especially these last 2 equations, we get C equals 0 and D equals a third. So we immediately get that from these two equations. And now we can simply go into these equations and solve for A and B. So if C is equal to 0, we can see that 2A plus 0 equals 1. So 2A equals 1, or A equals a half. And then if D is equal to a third, we're going to have 2B plus a third equals 0. So B is going to be a negative 1/6. So it looks like by choosing the entries A, B, C, and D thusly, I get a matrix that multiplies on the left and produces the identity. So that's my candidate. I'm going to call that matrix A prime. Okay, so that was designed to work on the right and produce the identity. Now what I need to do is I need to check to see if it also works when I multiply on the other side, on the left. So I have to check A prime times A to see if it also produces the identity. All right, let's see what we get. 1/2 times 2 is going to be 1, minus 0 or plus 0, so 1. 1/2 times 1 is a half. 3 times negative 1/6 is a minus 1/2, so 1/2 minus 1/2 is 0. 2 times 0 is 0, so that's 0 plus 0, so there's a 0 in that position. And we're going to get 0 plus 1, 1. So we found a matrix, first by finding a matrix that multiplies correctly on the right. So A times A prime is equal to the identity. And then we check to see if it also works on the other side. A prime times A is equal to the identity. And since this matrix A prime that we've produced satisfies both of these relationships, the matrix A is invertible. And A prime is an inverse for this matrix A. So we've tested both of these, and that proves the invertibility of the matrix A, and then we can declare A prime as an inverse for A. Okay, so that settles that question. A is definitely invertible. Now let's check this one. Let's see if this one is invertible. We're going to do the same strategy. We're going to see, can I multiply, let's say, on the right and produce a matrix which takes us to the identity. So let's set that up. So does such a matrix exist? Well, let's do exactly like we did in this problem. We're going to carry out the multiplication. We'll do that on the left, and we'll get ourselves a system of equations. And let's see what this is going to look like in this case. We'll have A minus C. We're going to have B minus D. We'll have minus 2A plus 2C. And then we're going to have minus 2B plus 2D. And these two matrices have to be equal if such a matrix is going to exist. And so we get a system of 4 equations. A minus C is equal to 1. We're going to get B minus D is equal to 0. We're going to get a minus 2A plus 2C equal to 0, and minus 2B plus 2D equals 1. So there's the 4 equations that we get by comparing elements on both sides of the equation. Now what I want you to focus on, we can do this in several ways, but I want you to focus on this relationship that's set up, let's say, between this pair of equations, these top equations on both sides. Let's look at this one. This one, we can take the a to the other side and cancel the 2. This equation here, let me number these just so I can kind of refer to them. If we concentrate on equation 3, the implication from equation 3 is that a is equal to c. Now when I take that and I put it into equation 1, we get the implication that c minus c is equal to 0, or 0 equals 1, which is a contradiction, right? And what that means is that this system of equations is inconsistent, and that means that there is no choice of A, B, C, and D that will ever solve this matrix equation. So the system is inconsistent. And the upshot of that is the matrix A is not invertible. Okay, so an important lesson coming out of this problem is that there really is something to test here, right? Unlike the real number system where every number other than 0 has an inverse, or every number in Z7 other than 0 has an inverse, there's a genuine problem here. Here we have two matrices, two 2x2 matrices, and without knowing anything deeper at this point in the course, they're rather indistinguishable from each other, but this one, for some reason, possesses an inverse matrix, and this one does not. So the question about whether, the question of whether a matrix possesses an inverse, is a matrix invertible, is a serious question, and we can see already that it is not the case just because I write down a non-zero square matrix that it has an inverse. This one has no inverse, and yet this one does. So there's quite a bit to explore here, right? What are the qualities of a matrix that allow it to have an inverse? What are the properties that make a matrix invertible? All right, so we'll continue to study this as we work our way through the notes, but already we should be attuned to the fact that not every matrix has an inverse, okay? So carry that thought with you. All right, let's head back to the class notes and learn some more. Theorem 3.6 tells us something very interesting about invertible matrices. It says, if A is an invertible matrix, then its inverse is unique. Now we'll use the following notation. If A is invertible, we will denote its unique inverse by a to the power of minus 1. So when we see a to the power of minus 1, that will stand for this unique inverse of the invertible matrix A. Now let's head over to the document camera and look at the proof of Theorem 3.6. All right, welcome to the document camera. We're going to prove Theorem 3.6. Now, Theorem 3.6 said that if A is an invertible matrix, then its inverse is unique. In other words, if it has an inverse, it has only one inverse. Now, we're going to prove the uniqueness of the inverse. And the tried and true method for doing this, and this is quite a beautiful proof, is to assume that there's more than one. Right? Let's start with the assumption that there are maybe a couple of matrices that could be inverses for the matrix A. So let B and C be inverses of the matrix A, and our goal is going to be to show that these are necessarily the same matrix, that they can't be different from each other. Now, let's just write down what this means. To say that B is an inverse of the matrix A is really saying two things. It's saying if I multiply B times A, I get the identity matrix. And if I multiply the matrices in the order A times B, I get the inverse matrix. So this is what it means to say that B is an inverse of A. Now let's do the same for C. C times A must give me the inverse, the identity matrix, and A times C must also give me the identity matrix. So that's what it means to say that C is an inverse of the matrix A. Now, I claim that from these four statements, we can show that B must equal C. All right? Now we're going to use properties of matrices along the way too, but these four statements along with properties of matrix multiplication will give us the conclusion that B is equal to C. And let's start out this way. We're going to start out with B. Now we know that B is equal to B times the identity matrix. All right? Now I'm going to go to my list here. I can freely substitute any one of these four relationships in place of the identity matrix because the identity matrix is equal to any one of these four multiplications. And the one I'm going to choose is this one here. I'm going to write the identity matrix as A times C. Okay, and I'm using this relationship here. I can equate the identity matrix with A times C. Now I'm going to use the associative property of matrix multiplication. I'm going to lift these parentheses up and place them on B times A. Okay, so I'm using the associative property here. And now I see B times A, and I go back to my list here, and I can see that B times A is also equal to the identity, so I can replace B times A by the identity matrix. And then finally, the identity matrix has the property that when it multiplies any matrix, it just leaves the matrix itself. And so we can see that B must in fact equal C, and that's our proof. If B and C are inverses of the matrix A, then B must equal C. There can only be one inverse matrix for a matrix if it's invertible at all. And according to what we set out in the notes, that inverse, that unique inverse is just going to be symbolized or denoted by A inverse. There's only one. If A is an invertible matrix, there is only one inverse, and this is going to be its symbol. Okay? All right, so I hope you enjoyed that. That's one of that's the kind of a very beautiful theorem, and it seems like you get something for nothing, but it's very kind of clever in how it's laid out, and you get this beautiful conclusion that just from the definition of an inverse of a matrix and properties of matrices that this matrix inverse, in fact, must be unique once you know it exists. All right, let's head back to the course notes and keep going. Now let's make a connection between systems of equations and matrix equations. So consider the system of equations that I've got shown here. This is 2 equations and 3 unknowns. And my claim is that that's equivalent to the matrix equation that's shown here. Let's just check to make sure that this makes sense. So here's a matrix which has 2 rows and 3 columns. Here's a matrix that has 3 rows and 1 column. We know that when we form this matrix product, that's going to give us a matrix with 2 rows and 1 column. And how am I going to get those 2 entries? I'm going to take the dot product of this first row against this column. And then I'm going to take the dot product of this row against this column. Let's see what we get. When I form this first dot product, I'm going to get 4x plus 5y plus 9z, and that's going to have to equal 14. And that's exactly what this first equation says. When I take my second row and dot it with this column, I'm going to get 2x plus 3y minus 11z, and by matrix equality, that's going to have to equal -8. And that's precisely what this second equation says. So in effect, we can write the system of equations as a matrix equation in the form A, the matrix of coefficients, times a column vector x, a matrix of unknowns, is equal to B, our matrix of constants. We can write this system of equations in the form A times x equals B. And now we're trying to solve this matrix equation for this unknown matrix X. Now this suggests that we can try to solve a system of equations by solving its corresponding matrix equation. And we can do this using the matrix inverse, provided that this matrix of coefficients is a square matrix. Now in this example, it is not a square matrix, so there would be no way to solve this matrix equation through a matrix inverse. But we could if this matrix of coefficients is a square matrix, and that means that the number of equations and the number of variables would have to be equal to each other. Now this situation is addressed in our next theorem, Theorem 3.7. If A is an invertible n by n matrix, then the system of linear equations given by ax equals b has a unique solution, namely x equals a inverse times b, and this is true for any b in n-dimensional space. Let's go to the document camera and look at the proof of Theorem 3.7. All right, welcome to the document camera. We're going to look at the proof of Theorem 3.7. It's a very important theorem, and it tells us something about the nature of systems of equations when our matrix of coefficients has an inverse. Now, what we have to show two things, right? First, that a system like this always has a solution. That's what we usually call the existence phase of this proof. So no matter which vector b you hand me, I know that there exists a solution to this system of equations. So there's kind of an a priori existence. I know that this system has a solution. And then phase two is to show that this system has only one solution, right? That there is a unique solution. So there is a solution and it is unique. All right, so let's look at the existence phase of this proof. And generally when you're trying to show that a solution exists at all, you just produce one and show that it works. So here's the solution that I'm going to produce. I'm going to say, I think that A inverse times B is a solution to this system of equations. In other words, you hand me this vector B, I'm just going to hit it on the left by A inverse, and I think that that's always going to be a solution to this system of equations. All right, now how do we test that? Well, we plug in A inverse B for x and we see if we get B. So let's do that. All right, so I'm plugging in A inverse B for x. So I have A times A inverse B. Now by the associative law of matrix multiplication, I can pick up those parentheses and I can think about multiplying A times A inverse and then multiplying by B. But A times A inverse is the identity matrix. And the identity matrix times B is just B. And so this shows that this, in fact, is a solution to this matrix equation. When I apply A on the left, I get B. So A times A inverse B equals B. This is a solution. Now we know when we study systems of equations that it's possible that there are no solutions. It's possible that there is a unique solution, or it's possible that there are infinitely many solutions. So all we've demonstrated so far is that there is a solution, that this system of equations is consistent. Now we have to show that this solution is unique. All right. Now what we're going to do, and this is very typical for the uniqueness phase, we're going to say let y be any solution of the equation ax equals b. Now what does that mean? It means when I replace x by y, all right, now what I have to show you is that this vector y has to be A inverse b, that there is no choice. So I'm assuming at this point that y could be any solution to this system of equations or this matrix equation. But now I want to show you that I'm forced to conclude that it's of the form A inverse b, that all solutions have to come back to A inverse b. Let's see how that phase goes. So we're assuming that this is true. We're assuming that A times y equals the matrix B. Now I'm going to multiply both sides by A inverse. All right. Now again, we're going to use the associative law. But A inverse times A, is equal to the identity matrix. And that means since the identity matrix times y is just equal to y, this implies that y is of the form A inverse B. So we're drawn back to exactly the same solution. In other words, assuming that there is some other solution out there, we can plug it into our equation, But then by applying the inverse, we can show that we're just back to the same solution that we had before. Everything is drawn back to exactly that same solution. So phase one, a solution exists, A inverse B. Phase two, if I assume that there's another solution out there, I'm led to the conclusion that it too is of the form A inverse B. Therefore, the solution is unique. It's the only one out there. Okay, so this is a really super important property of looking at matrix equations from systems of equations, if you will, where the coefficient matrix is invertible. So let's remember this property of matrix equations. This will come back later in this section in a big way. So right now we understand it hopefully, and we'll see how it kind of fits into a grander scheme as we work our way through this section. Our previous result, theorem 3.7, is only helpful if it's easy to find the inverse of a matrix, and in general, that's not true. However, it is easy to find the inverse of a 2 by 2 matrix, and that's what's being addressed here in theorem 3.8. So theorem 3.8 says, suppose you have a 2 by 2 matrix A with entries A, B, C, and D. Then A is invertible if AD minus BC does not equal 0. Now, hopefully this difference of products looks familiar to you. This is the determinant of this 2 by 2 matrix. We take AD minus BC. If that determinant is not equal to 0, then this matrix A is invertible, and its inverse takes this form. We have 1 over that determinant times this matrix here, and we can think of this matrix as being easily derived from the original matrix by simply swapping the elements on the main diagonal, so A and D exchange positions, and these off-diagonal entries have their signs changed. So we swap the elements on the main diagonal and change the signs of the elements on the off-diagonal. So that's how we can easily construct the inverse matrix from the matrix A under the condition that AD minus BC is not equal to 0. Now, if AD minus BC is equal to 0, in other words, if the determinant of that matrix is equal to 0, then A is not invertible. Now, let's go to the document camera and look at the proof of theorem 3.8. All right, welcome to the document camera. We're going to look at the proof of theorem 3.8, and there are really two separate directions in the proof of theorem 3.8. The first part is to assume that this determinant AD minus BC is different from 0, and then knowing that, show that the matrix A is invertible, and in fact that we're going to show that the inverse takes on a special form. But the assumption here in this first part is that AD minus BC does not equal 0. Now what we're going to do is we're going to look at a special matrix. Let's call it A prime. And it's leveraging the fact that AD minus BC does not equal 0, because I'm going to divide by AD minus BC. So 1 over AD minus BC. That makes sense because this is not I'm not dividing by 0. And then I want to form a 2 by 2 matrix that I get by taking the original matrix, A, B, C, D, and flipping the diagonal elements and changing the signs in the off-diagonal positions. I'm going to call that matrix, right now I'm going to call it A prime. I'm going to show that it's the inverse, but right now I'm just thinking of it as a candidate for the inverse. We don't know that it's the inverse yet, so we're not going to name it that yet. But we're going to check. We're going to multiply A times A prime, and then we're going to multiply A prime times A, and we're going to show that in both cases we get the 2 by 2 identity matrix. So let's look at this direction first. Let's do A times A prime, and I'm going to leave this scalar out in front. So that's one of our properties of matrix multiplication. We can kind of do all our scaling at the end. I'm going to first write the matrix A. Then I'm going to write this other part of A prime. And then I need to work out this matrix product. I'm going to leave that scalar out in front. Now let's look at the entries of the product. I'm going to have AD minus BC. I'm going to have a minus AB and a plus AB. A CD minus CD. Minus BC plus AD. That's another AD minus BC. Now I can bring my scaling inside and scale all of the elements by 1 over AD minus BC. That's going to turn this into a 1 and that into a 1. These will remain 0. And so that shows that at least if I multiply in the order A times A prime, I get the 2 by 2 identity matrix. Now let's check the other direction. We'll put A prime on the left this time. And again, I can bring that scaling out in front. And now I'm going to write them with this matrix first. I'll put A here. All right, let's check all the entries. We'll have AD minus BC. We'll have DB minus DB. Minus AC plus AC. And then a minus BC plus AD. That's AD minus BC. And then again, by scaling all of the elements by this, I'm going to get 1, 0, 0, 1. Okay, now if we just look at our definition of what it means to be invertible, we've shown that there's a matrix. We're calling it A prime. When I multiply on the right, I get the identity. When I multiply on the left, I get the identity. And that means that A is invertible. We know there's only one matrix that can do this, and that must be the inverse. So one other consequence from this is that this matrix A prime that's doing this work for us must be the inverse of A. So we can identify A inverse now as A prime. And that's the first part of the proof of theorem 3.8, that the non-zero determinant gets the ball rolling. Once the determinant is different from 0, the matrix is invertible, and we can write down the inverse very simply. And now we have to show the second half of theorem 3.8. And I've already kind of front-loaded this a little bit just to save us a little bit of time here under the document camera. But the assumption in the second half of theorem 3.8 is that this determinant is equal to 0. And we have to show that whenever this is the case, right, when AD minus BC is equal to 0, we have to show that that implies that A is not invertible. Now, what does that mean effectively? It means that there would be no choice of X, Y, Z, and W. This is going to form some candidate matrix A prime. There is no way to configure this matrix so that A times A prime equals the 2 by 2 identity matrix. We have to show that as a set of equations in X, Y, Z, and W, that this is always inconsistent under this assumption. So this assumption is going to force the inconsistency of this set of equations in X, Y, Z, and W. Now, how can we think of this as a set of equations in X, Y, Z, and W? The easiest thing to do is just to imagine multiplying out this pair of matrices here on the left and equating entry by entry the entries of this side with the entries of this side and getting 4 equations. So for example, we'll get AX plus BZ has to equal 1. We'll get AY plus BW has to equal 0. We'll have CX plus BDZ has to equal 0. And then finally, CY plus DW equals 1. Now we have to show that under this assumption, there's no way to get a consistent, this is not a consistent set of equations. We have to show that there's always an incoherence or contradiction built into this system of equations. Now, we have to work through some annoying cases. There's really only one interesting case, one case that is truly beautiful and stunning. The first two are kind of annoying. So let's look at those first and kind of dispense with those cases. So the first case you have to consider is, what if this number a is equal to 0? So let's look at that. So let's suppose that a is equal to 0. Now, if a is equal to 0, then this determinant equation just says b times c is equal to 0, right? So if a is equal to 0, we know that this implies that b times c is equal to 0. And that means that either b is 0 or c is 0, possibly both, but one or the other of them has to be equal to 0. So there's really like two possibilities. A is equal to 0 and b is equal to 0, or a is equal to 0 and c is equal to 0. So let's look at those two branches off of this first case. So a could equal 0 and b could equal 0, or a could equal 0 and c could equal 0. Let's look at the consequences of both of these, okay? Now, if a is equal to 0 and b is equal to 0, let's look at equation 1. In equation 1 here, we would have a equal to 0 and b equal to 0. So equation 1 would read 0x plus 0z is equal to 1, and that's a contradiction. That's an inconsistency. So that's inconsistent. Let's look at the case. Now, this one's a little more complicated, but let's look at the case where a is equal to 0 and c is equal to 0. Now, if we look at equation 1, right, and 2, we're going to be able to get something out of this, because if a is equal to 0 and c is equal to 0, then equation 1 boils down to b times z is equal to 1, and d times z is equal to 0. Okay, now, if these two numbers, b and z, are both multiplying to 1, neither one of them can be 0, right? Neither b nor z can be equal to 0. In particular, z is not equal to 0. But if z is not equal to 0, this implies that d is equal to 0. Okay, so once again, b times z equal 1 means neither b nor z is equal to 0. But if z is not equal to 0, then d must equal 0 according to this equation. So now we know that d is equal to 0. So now we know that c is equal to 0 and d is equal to 0, and we can look at equation 4, and we can see that we get a contradiction, because equation 4 would now read 0y plus 0w is equal to 1, which is a contradiction. All right? So we find that whenever a is equal to 0, we're led to something contradictory in these equations. There's an inherent incoherence here in these equations. Now, there's a second case that we would need to explore this in gory detail, but since it parallels this one so nicely, I'll mention it, and you can work out, if you want to, all of these kind of details. That second case that we would have to kind of address would be the case where c is equal to 0. And I'm claiming that it's going to be much like this. This is going to lead to incoherence. So this is also going to produce inconsistency in the system. So in case 3, I'm going to assume that a is not equal to 0 and c is not equal to 0, because I know that in either of those cases I have an inconsistency. So in my third case, I'm going to assume that a does not equal 0 and c does not equal 0. And I'm going to show you in this case, you also get inconsistency. Now, in this case, all we have to do is, let's say, pick on equations 1 and 2. So let's rewrite equations 1 and 2 down here. Now, what I want to do is multiply this first equation by c, and I want to multiply this second equation by a. Now, that's fine, right? Because neither A nor C is equal to 0. So I'm multiplying both of these equations by non-zero scalars. All right, so the transformed equation 1, let's call it 1 prime. I'm multiplying by C, so it's going to look like ACX plus BCZ equals C. The transformed equation 2, when I multiply by A, is going to look like ACX plus ADZ equals 0. So I've transformed equation 2 by multiplying by a non-zero number. And now what I'm going to do is I'm going to take equation 2 and subtract equation 2 prime and subtract equation 1 prime. So I'm going to subtract these equations and I'm going to eliminate this variable x. All right, so let's do that. On this left-hand side, I can factor out the common z. And on this right-hand side, I'll have 0 minus c. So I get this equation, AD minus BCZ equals negative c. Well, this is equal to 0. So this product on the right is 0 times z. And on the right, I've got negative c, and c is not equal to 0. So I have something equal to 0 equal to something that's not equal to 0. And this is an inconsistency. Okay, so if we look at the argument kind of in a broad overview, we're assuming that AD minus BC is equal to 0, and we want to show that A is not invertible, which is equivalent to showing that this system is inconsistent, which is equivalent to showing that this set of 4 equations is inconsistent. In other words, there's always a built-in incoherence or inconsistency in this system of equations. We looked at the case where possibly A was equal to 0, and we showed that produces an inconsistency or an incoherence, a contradiction. We looked at the case where C is equal to 0, and we said it's going to be very much like this case. That's going to always have its own internal inconsistencies or incoherences. And then finally we said, well, if A is different from 0 and C is different from 0, let's look at that case. And when we looked at that case, we showed that the AD minus BC condition comes in here by looking at this system of equations, and that is assumed equal to 0. And so we get 0 on the left equals something non-zero on the right, and that's an inconsistency. So the assumption that the determinant is equal to 0 always produces an inconsistent system, and there is no matrix A prime that will allow us to take A times A prime equals the identity matrix. Therefore, A is not invertible. And there's our complete proof of theorem 3.8. All right, let's head back to the class notes and keep going. Now let's work a problem that puts some of our theory to use. I want us to express the system of equations as a matrix equation, and then I want us to solve the matrix equation through the inverse. So join me at the document camera for the solution to this problem. All right, welcome to the document camera. Our goal is to first express the system of equations as a matrix equation, and then to see if you can solve the equation through the matrix inverse. So we're going to check that matrix of coefficients, see if it's invertible, and if it is, then we can solve the system of equations using that matrix inverse. So putting this into a matrix equation is relatively straightforward. We can basically just lift it right out of the equations here. We're going to have a matrix of coefficients, 4, 5, 2, 3. We can form a column vector or a matrix, which is a 2-by-1 matrix consisting of the unknowns, x and y. And then we can form another column, which again is another 2-by-1 matrix consisting of these constants, the 14 and the negative 8. All right. Let's just think of this as capital A. We'll call that one X, and we'll call this one B. Now, if A is invertible, then we can solve this matrix equation by multiplying both sides by A inverse on the left, and we can write our solution as X equals A inverse times B. And we can do that matrix multiplication and work out our matrix X, and we can identify little x and little y. So that's the strategy. Now we have to test for the invertibility of A, right? Is A invertible? And we have an easy test for a 2 by 2 matrix. We simply have to check its determinant. So we're going to check the determinant of A is what I get by first multiplying along the main diagonal and then subtracting the multiplication along this off diagonal. So it's going to be 12 minus 10, which is 2, which is different from 0. And so that's the test. As long as this determinant is something other than 0, the matrix is invertible. So yes, the answer is A is invertible. And we've already got the determinant calculated. We know how to get the inverse for a 2 by 2 matrix. It's going to be simply 1 over that determinant. And then what do? I take my diagonal elements, the 3 and the 4, and I exchange them. So the 3 goes here, the 4 goes here. And I take my off diagonal elements and I negate them. Okay, so that's the inverse. The last step is to solve this equation by multiplying on both sides by A inverse on the left. So the solution is going to be x equals A inverse times B, which in this case is going to be, I don't want to forget my 1/2. I'll have the scalar 1/2, the 3, the -5, the -2, and the 4, the 14, and the -8. Now there's several things you can do here. Again, I think there's 3 choices you can make. Leave the scalar out, just bring it in at the end, do the multiplication first. Or since this scalar might play nicely with the elements in the matrix, you might scale the elements of the matrix. That's going to introduce fractions. But I noticed that the entries of the column B are both even, and so the scalar will work nicely with that column. So I'm going to bring that scalar in to this second matrix. I'll scale it, and I'll get a 7 and a -4. And now I'll do the matrix multiplication. So I think there's at least 3 things you can do there, all of which would make sense, right? Now I just have to do this matrix multiplication. I'm going to have a 21 plus a 20, which is going to give me 41. I'm going to have a -14 plus a -16. That's a -30. And that has to equal our column matrix or our column vector x, right? And we know the entries are x and y, so this is telling me that x is equal to 41 and y is equal to -30. And so there's a way of solving the system of equations that's different from what we were doing before. And then instead of doing augmented matrix and row reduction and getting it down into reduced row echelon form, this is a slightly different approach. We can quickly check a 2 by 2 matrix to see if it's invertible. We can form its inverse, and we can solve this system of equations, this matrix equation, through the inverse matrix. So hopefully that was gives you some insight into how we can use the matrix inverse to solve a system of equations. Let's work one more problem using our theory. In each case, solve the equation AX equals B for the unknown X. In part 1, we've got A is a 2 by 2 matrix and B is a 2 by 1 matrix. And in part 2, we have A is a 2 by 2 matrix and B is a 2 by 2 matrix. Let's go to the document camera and see how we can use our theory to solve the equations AX equals B in both cases. All right, so in this problem, we're going to put some of our theory to use. In both cases, we want to solve an equation AX equals B for this unknown X given the data. In this case, A is this 2 by 2 matrix and B is this 2 by 1 matrix. And the same thing here in problem 2. The only wrinkle here is that A is a 2 by 2 matrix and so is B. So in this problem, X is going to be another 2 by 1 matrix. And in this problem, X is going to be a 2 by 2 matrix. Now that's just going to come out in the solution. So we'll see that kind of reveal itself. Now, what we know is that we can solve both of these equations very simply if A is invertible. So let's just check to see if, let's work problem 1. Let's check to see the invertibility condition. So the AD minus BC condition, the determinant condition, is going to be, in this case, 6 minus 4 which is equal to 2, which is not equal to 0. So we know that A is invertible, and in fact, we know that A inverse has a particularly simple form. It's going to be 1 over 2. And then we're going to get the rest of the inverse by just flipping the main diagonal. So it'll be 2, 3 on the main diagonal, and changing the signs on the off diagonal. So there's the 2 by 2 inverse. So in this first equation, we can say that the solution is x is going to be the inverse of A times the matrix B. And in this case, that's going to be 1/2, 2, -1, -4, 3, multiplying 4, 2. Now, I'm just going to leave the scalar out in front here and do all my matrix multiplication first. So let's see what we get. We're going to get 8 minus 2, which is 6. And then we'll have a -16 plus 6. A -16 plus 6 will be a -10. And then I can scale this column at the end, and I'll have 3 and -5. And that's my unknown vector x. All right, so that's pretty nice. Let's do it, problem 2. We're going to check the determinant. We'll check this AD minus BC condition. So the determinant of our matrix A is going to be 9 minus 8, which is equal to 1, which is not equal to 0. That's the most important thing. And it's nice when this is equal to 1 because it makes the inverse particularly simple. We'll just have 1 over 1, so we'll have 1 out in front. I'm going to switch the diagonals, which in this case will not appear to be any change at all, and I'll change the signs on these off diagonal positions. So the matrix is invertible, and this is its inverse. And now we simply have to solve this equation by multiplying both sides on the left by A inverse. So x will be A inverse times B. In this case, that's going to be a product of two 2 by 2 matrices. Okay, now we have to work out the elements of the product. Let's see what we're going to get. We're going to get 12 plus a -4. 12 plus a -4 is going to be 8. We'll have 15 plus 12. That's going to be 27. We'll have a -16 plus 6, -10. And then finally a -20 minus 18. That's a -38. And so we find that our unknown matrix X in this original equation must be this 2 by 2 matrix down here. Okay, so hopefully that reinforces some of the theory we've been working on, how to solve these kind of simple equations through the matrix inverse. All right, let's head back to the class notes. Now let's study some important properties of invertible matrices. And these properties are embedded in Theorem 3.9. So Theorem 3.9 contains 5 important properties of invertible matrices. Let's look at property A. If A is an invertible matrix, then A inverse is itself an invertible matrix, and in fact, the inverse of the inverse is just the matrix A itself. If A is an invertible matrix and C is a non-zero scalar, then property B says that C times A is itself an invertible matrix, and the inverse of C times A is what we get by taking the reciprocal of C and multiplying it by the inverse of A. Let's take a look at property C, a very important property. It says if A and B are invertible matrices of the same size, then their product A times B is also an invertible matrix, and the inverse of A times B is simply the product of their inverses, very importantly, taken in reverse order. So the inverse of A times B is B inverse times A inverse. If A is an invertible matrix, then its transpose is invertible as well. And in fact, the inverse of the transpose is the same as the transpose of the inverse. That's property D. And finally, property E. If A is an invertible matrix, then a to the power of n is also an invertible matrix for all non-negative integers n. And in fact, the inverse of the nth power of a is equal to the nth power of the inverse of a. Now what I want to do is go to the document camera and show you the proofs for C and D. And once you see those proofs for C and D, I would encourage you to leverage those techniques and try to prove A, B, and E for yourself. So let's head over to the document camera and look at the proofs of C and D of Theorem 3.9. All right, we want to prove properties C and D of Theorem 3.9. And I'll do these next to each other. I'll do a property C here and property D here. Let's just remind ourselves of what property C is saying. It says if A is invertible and if a matrix B is invertible, then their product A times B is invertible. Now all I have to do is show that there's a matrix that multiplies on the right with AB and produces the identity, and simultaneously multiplies on the left with AB and produces the identity. And my candidate is going to be B inverse times A inverse in that order. So let's see if that actually works. So suppose I want to multiply AB by B inverse A inverse. Let's see what that does. Now, again, we're going to use a pretty nice property of matrix multiplication, which is the associative principle. In effect, I've got four multiplications here. I'm free to pick up these parentheses and associate them in any way that I want. And what I'm going to do is first do this middle multiplication. So I'm going to write this as A, B times B inverse, A inverse. All right. Now, when you do B times B inverse, you're going to get the identity. So this reduces to A times the identity times A inverse. And again, I'm free to associate this any way I want. So I'll first do this multiplication. Now when I do A times the identity matrix, I just get the matrix A. So that's just A. And now I'm down to the matrix multiplication of A against its inverse, and that's the identity matrix. Okay, so we've shown that this candidate matrix multiplies on the right with AB and it produces the identity matrix. I just need to flip it to the other side and see what happens. But if you're kind of looking ahead, you can see that you're probably already on to me into what I'm going to do next. So I'm going to put B inverse, A inverse on this side and AB on this side. And let's see what we get. We'll use the associative law. In the middle, I'll have A inverse times A, and then B. This is going to multiply to the identity. And I'm free to think of this next operation in any pairing. Let me pair them up this way. B inverse times the identity, of course, is just B inverse. And B inverse times B is just the identity matrix. So our matrix, which we seem to pull out of thin air, multiplies AB on the right and produces the identity. It multiplies AB on the left and produces the identity. And that alone, the existence of a matrix that does this already says that A times B is invertible. Right? But we know more than that. Since this is the matrix that takes AB to the identity, it must be that that is the inverse matrix. So not only is AB invertible, we know that the inverse of AB must be this matrix B inverse A inverse. Okay, so that's the result that we wanted to show. And that's the famous property C of the existence of the inverse for the product of two invertible matrices. That's a beautiful result. Now, let's look at this result D, and it's going to have, formally, it's going to look very similar to what we just did. And now using properties of the transpose. Now, what do we know? We know that in this case D, we're asserting that A is an invertible matrix, and we want to show that its transpose is invertible. And I'm going to do much the same thing I did here. I want to test the invertibility of the transpose, so I have to manufacture some matrix that I can multiply on the right and multiply on the left of A transpose and generate the identity matrix through that multiplication. So here's my candidate matrix. I'm going to start with multiplying on the right. I'm going to take A transpose, and I'm going to multiply it by a matrix, which I get by first inverting A and then taking its transpose. All right, that's going to be my candidate. Now let's see what happens. We know that if I have a product of transposes, that I can write them as a product transposed. So this is one of the properties of a transpose. I can think of this as a single transpose that acts on the product of these two matrices. And we have to be careful. We have to take them in the reverse order inside the transpose. So this will appear inside the transpose with A inverse on the left and A on the right. Normally we think of this property as going in this direction, right? We take the product of two matrices, we take the transpose, we can apply the transpose to the separate pieces, but we have to remember to flip their order. So we typically write this law in this direction, but it applies obviously in this direction as well. Now, what have we won by doing that? By writing a single transpose and writing this product inside, we now have A inverse times A, which is the identity. And the transpose of the identity, it is not hard to see that that is, again, just the identity matrix, because the rows and columns of an identity matrix, row 1 is equivalent to column 1, etc. So it has the property that it's symmetric, obviously, and it's its own transpose. Okay, now let's look at multiplying this matrix on the other side. So I take my A inverse transpose, I put it on the left of A transpose, but the same law applies. I can write this as a product of matrices with the transpose on the outside. I just have to remember that when I insert them in here that I have to flip the order in which they appear outside here. So I'll have A on the left and A inverse on the right inside the transpose. Now that still multiplies to the identity matrix. The identity matrix is symmetric, so this is just going to be the identity matrix, and we're done. This shows that A transpose is invertible. And more than that, since we know that this is the matrix that multiplies A transpose to the identity on both sides, we also have, as an artifact of this proof, that A transpose inverse must be the transpose of the inverse. That's what we've shown, right? That A transpose's inverse follows this formula. Okay, now of course this has a nice look to it, right? It just looks like you can take the transpose and the inverse and flip the order in which they appear. And that is a nice visual cue, right? If I see it in A transpose inverse, I can imagine just reversing the role of the inverse and the transpose. And that's a true statement. And it's kind of a helpful way to kind of visualize or think of that property D. Okay, so those are two very nice and deep properties of matrices and their inverses. And I would encourage you to take this and now try your hands at A and B and E and see if you can work out proofs for A, B, and E. Our next definition extends the notion of a negative power at least to the class of invertible matrices. So if A is an invertible matrix and N is a positive integer, then A to the power of negative N is defined by A to the power of negative N is equal to either the inverse of A to the power of N, or by property E of theorem 3.9, the nth power of A raised to the power of -1. So either of these can stand for the definition of A to the power of -n. Now, let's put this to work. Let's take a look at this problem here. A is this 2 by 2 matrix. Let's find A to the power of -4. So join me at the document camera for the solution to this problem. All right, let's take a look at the solution to this problem. We've been given a matrix A, and we want to find A to the power of -4. Now, there's two different ways that we can think about this according to the work that we've done so far, right? According to the definition of A to the power of -4. We can either think of it as the inverse matrix of A to the power of 4, That would be one way to think about it. Or equivalently, we could think about it as the fourth power of A inverse. And it's, without going into some kind of preliminary work, it would be hard to know if one of these ways is easier than another. Let's investigate doing it this way just to see what the inverse matrix looks like and think about computing its fourth power. All right, so the inverse matrix for this matrix, it's a 2 by 2 matrix, so we can just check the determinant. We're going to get 2 minus 1. And that's equal to 1, and that's very nice. It's not equal to 0, and it gives us a nice appealing inverse matrix. So it's going to be 1 over 1. We're going to switch the diagonal elements, reverse their positions, and change the signs in these off-diagonal positions. So we're off to a good start. A inverse has this fairly simple form. So this looks like it's going to be a promising approach to this problem. Now, we're working up to the fourth power. Let's work out the square of this matrix. So let's do A inverse squared, and that'll simply be what I get. By multiplying them together in this fashion. All right, let's check out and let's see what we get. We're going to get 1 plus 1 or 2. We'll get negative 1 minus 2, so that's negative 3. We'll get negative 1, a negative 2, so negative 3, and then 1 plus 4 or 5. So there's the square of A inverse. Now we have to calculate the inverse of A to the fourth power, and we can simply think of that as the inverse of A squared times the inverse of A squared. And so I just have to take the matrix we've just calculated and juxtapose it. And work out this product. This will be our final answer. So we've got the fourth power rendered as the product of the two squares. All right, let's see what we get. We're going to get 4 plus 9, and that's going to be 13. We'll have a negative 6 minus 15. That's a negative 21. We'll have a negative 6 and a negative 15. That's a minus 21. And then finally, we'll have a 9 plus a 25. A 9 and a 25 will give us a 34. And so that's how we can work out the fourth power. We can work out A to the negative 4 by working out the fourth power of A inverse. And so that's the answer. We could have easily gone this way. We worked out A to the fourth first and then worked out its inverse. But this way worked just fine because the inverse wasn't so bad to calculate. All right, great. So let's head back to the course notes and carry on. In this next problem, we're going to put a lot of our properties of invertible matrices to use. So let A, B, and X be invertible matrices of the same size. Let's solve the equation below for X. So join me at the document camera and let's look at how we can use all of our properties of matrices to solve this equation for the unknown matrix X. All right, welcome to the document camera. We're going to solve this matrix equation for the matrix X. And what I'm going to do is simplify the left-hand side a little bit, and I'll do the same on the right-hand side, and then we'll look at that simplified equation and we'll solve for the unknown matrix X. So let's think about this left-hand side. We're presented with A inverse times X inverse inverse. And by one of our properties of the inverse, we can apply the inverse to each of these parts, provided we commute them. So this will be the same as X inverse inverse times A inverse inverse. By another property of the inverse of the inverse is just the matrix itself. So we just get X. And by that same property, this just becomes the matrix A. So after a couple of steps, we can see that this left-hand side reduces down to X times A. Now let's do a little bit of work on this right-hand side. again, we're presented with a times b to the minus 2 times a inverse. Okay? Now, we can use exactly the same step we did here. We can take this inverse and apply it to each of these parts, provided that we commute the multiplication. So we can write this as a times, I'm going to put some big parentheses here. Inside here, I'm going to have a inverse and then b to the minus 2 inverse. Now, the first thing I'm going to do, there's a couple of steps remaining here to simplify this. The first thing I'm going to do is pull up these outside parentheses and reapply them to a times a inverse. So I'm using my associative property here. And then I want to notice that a times a inverse is just the identity matrix. Okay, and now I want to use the fact that I can think of b to the negative 2 power in a couple of different ways, but one interpretation of that is it's b squared to the negative 1. Okay, so multiplying by the identity leaves the matrix unchanged, and b to the negative 2 is b squared to the negative 1 power, and now I can use the fact that the inverse of the inverse is just the matrix itself, so this is just b squared. Okay, so what we've shown is that the left-hand side can be written as x times a, and the right-hand side can be simplified down to simply b squared. And now I still have to solve for x. I'm going to multiply on the right on both sides by a inverse. And once again, I can reassociate and think of this as x times a inverse. Finally, this is the identity matrix. And then the identity matrix times x. X times the identity matrix is just x. And that's our final solution. So that brings a close to what I wanted to show you in this first part of section 3.3. So that closes part A, and now we'll show you, we'll pick up and finish the rest of section 3.3 in part B. So until I see you again at that next video lecture, take care of yourself and be good.